Our story begins not on Earth, but in the vastness of space, billions of years ago. Imagine a time when the universe was still young, filled with countless stars and galaxies, each with its own unique story. Picture a star much larger than our own sun, reaching the end of its life. This star, after burning brightly for millions of years, is now in its final stages. It explodes in a brilliant supernova, scattering its remnants across the cosmos. This explosion is one of the most powerful events in the universe, sending shockwaves through space. These remnants, clouds of dust and gas, are the building blocks of our solar system. They float through space, waiting for the right conditions to come together. This swirling cloud, known as the solar nebula, is where our journey truly begins. Within this nebula, countless particles and gases start to interact. Driven by gravity, the nebula begins to collapse in on itself. This gravitational pull causes the nebula to shrink and condense. As it collapses, it starts to spin faster and faster. This spinning motion flattens the nebula into a disk shape, with most of the material gathering in the center. The center, where most of the mass gathers, becomes incredibly hot and dense. This core, under immense pressure, begins to glow brightly. Eventually, this dense core ignites, giving birth to our sun. This new star will be the heart of our solar system, providing light and warmth. Away from the intense heat of the nascent sun, the remaining dust and gas continue to swirl. These materials, though far from the sun, are crucial for the formation of planets. This material, remnants of the supernova, contains all the elements that will one day make up our planet and even ourselves. Elements like carbon, oxygen, and iron are all present in this cosmic soup. Tiny particles, drawn together by electrostatic forces, begin to clump together. These initial clumps are the seeds of future planets. Over millions of years, these clumps grow larger and larger. Through a process called accretion, they attract more material, eventually forming planetesimals, the building blocks of planets. These growing clumps, called planetesimals, are the seeds of planets. They start as tiny particles of dust and ice, gradually sticking together through electrostatic forces. Over time, these small particles form larger and larger clumps. They collide and stick together in a process called accretion. This process is driven by the gravitational pull of the growing planetesimals, which attracts more material to them. As they grow, their gravitational influence increases, pulling in even more debris from the surrounding space. Some planetesimals grow larger, their gravitational pull attracting even more material. This gravitational pull is crucial, as it allows the planetesimals to gather enough mass to eventually become protoplanets. These protoplanets are the building blocks of the planets we see today. In the chaotic dance of the early solar system, these planetesimals are constantly colliding, some shattering into pieces, others merging to form larger bodies. This constant collision and merging process is a violent and dynamic phase shaping the future planets. Over millions of years, this process of accretion shapes the early solar system. The gradual accumulation of material leads to the formation of larger and more stable bodies, setting the stage for the development of planets, moons, and other celestial objects. Close to the Sun, where temperatures are high, rocky planets like Mercury, Venus, Earth, and Mars begin to form. These planets are composed mainly of heavier elements that can withstand the intense heat near the Sun. These rocky planets, built from the heavier elements in the solar nebula, are the first step towards the familiar solar system we know today. Their formation marks the beginning of a complex and intricate process that will eventually lead to the diverse planetary system we observe. The early Earth, a ball of molten rock, is a far cry from the planet we know today. Its surface is constantly reshaped by volcanic activity and impacts from other celestial bodies. Bombarded by asteroids and comets, the young planet absorbs these impacts, incorporating their material into its own. These impacts play a significant role in delivering essential elements and compounds to the Earth's surface. This period of intense bombardment, known as the Late Heavy Bombardment, plays a crucial role in shaping the Earth's surface and potentially delivering water to our planet. The impacts create craters and basins which may have been filled with water, setting the stage for the development of life. The constant bombardment, combined with the heat generated by radioactive decay within the Earth itself, melts the planet's interior. This molten state is crucial for the next stage of Earth's evolution differentiation. In this process, denser materials like iron and nickel sink towards the center, forming the Earth's core. This molten, churning Earth is a scene of intense geological activity. Volcanoes erupt, spewing lava and gases into the early atmosphere. The surface, constantly bombarded and reshaped, is a hostile and alien landscape. Yet, within this chaos, the seeds of our planet's future are being sown. Section 4 layered up how Earth found its structure. As the Earth cools, the molten material begins to solidify. Lighter elements like silicon and oxygen rise towards the surface, forming the Earth's crust. Between the core and the crust lies the mantle, a thick layer of hot, viscous rock. This layered structure, formed through the process of differentiation, is crucial for the development of plate tectonics, a defining feature of our planet. This layered structure is not static. The Earth's interior is still incredibly hot, and this heat drives convection currents in the mantle. These currents, much like the currents in a pot of boiling water, cause the Earth's tectonic plates to move and collide, shaping the planet's surface over millions of years. Section 5, a cosmic dance, the Moon's formation. The early solar system is a chaotic place, and the Earth's story takes another dramatic turn. A Mars-sized object named Theia collides with the young Earth in a cataclysmic event. This impact, known as the giant impact hypothesis, is thought to be responsible for the formation of our Moon. The impact throws a tremendous amount of debris into orbit around the Earth. Over time, this debris coalesces, drawn together by gravity, forming the Moon. The Moon's size and composition, as well as the Earth's tilted axis, provide compelling evidence for this giant impact. Section 6. Shifting sands of time plate tectonics and its impact. The Earth's crust, now solidified, is not a single unbroken shell. It is broken into several large pieces called tectonic plates. These plates, floating on the semi-molten mantle, are in constant motion, driven by the convection currents within the Earth. Where plates collide, mountains rise, volcanoes erupt, and earthquakes shake the ground. This constant movement, known as plate tectonics, is a defining feature of our planet. It is responsible for the continent's shapes, the formation of mountain ranges, and the ongoing geological activity that shapes our world. Without plate tectonics, Earth would be a very different place. Section 7. The Blue Oasis, the genesis of oceans and conditions for life. As the Earth cools further, water vapor released from volcanic eruptions begins to condense in the atmosphere. This process is crucial as it marks the beginning of a significant transformation on our planet. The steam and gases from these eruptions play a vital role in creating the early atmosphere. This condensation leads to rainfall, and over millions of years, rainwater accumulates in the lowest parts of the Earth's surface, forming the oceans. These early rains were relentless, carving out valleys and filling basins, creating the first bodies of water that would eventually become our vast oceans. These early oceans, initially acidic, gradually become more hospitable to life. Over time, the chemical composition of the water changes, neutralizing the acidity and allowing for the development of more complex molecules. This transformation is essential for the next stages of life's evolution. The stage is now set for the emergence of life. Microscopic organisms begin to appear, thriving in the nutrient-rich waters. These simple life forms are the ancestors of all life on Earth, marking the dawn of biological activity on our planet. With liquid water, a protective atmosphere, and a source of energy from the sun, the Earth is transformed from a hostile ball of rock into a cradle for life. The interaction between sunlight and water drives essential chemical reactions, fostering the growth and diversification of early life forms. The story of how life first arose on our planet is a story for another time, but it is a story that begins with the dramatic events that formed our Earth. These early conditions set the stage for the incredible diversity of life we see today, making our planet a unique blue oasis in the vastness of space.